It seems that you are using two modules, so one for the self-supervised learning part and one for the supervised learning part. So I'm wondering, is there any possibility that we can combine those two tests into one module? For example, we can use one transformer for both the self-supervised learning part as a pre-training part, and for the supervised part, which is for the main test, as a fine-tuning part.
Yes. First, do a self-supervised, then for each downstream task, we do the a model for the. So this idea actually is before the. We do this in 2000 or maybe it's before the large language model. For the large language model, I think it's something like what you just mentioned. It's not just this unsupervised, self-supervised and supervised are separate. They may combine together, use this supervised information to fine-tune the representation. Like the ChatGPT, actually, although we don't know exactly how they do, but from what we can guess, also from the Lambda. The Google release Lambda is open source. We know they have the self-supervised part. Also, they have the supervised part. They use the supervised to fine-tune. Yeah, definitely that would be. I think that may give a better result. But we did this before the large language model become popular.
So that would be a possible solutions. And for your experiment, you are using two separate models, right?
Yes. I think definitely, if anyone interested to doing research, you can follow this idea.
Thank you.
I'm not sure if anyone did this. I didn't say paper doing that.
Thank you very much.
Yeah, very good question.
Hi, just you mentioned about the context window. Is the window size of the context window the same as the sliding window in MLP? Like the
Yes,
is the same. So
it's same concept.
Same concept. Is that so? The it's also hyperparameters you need to
Yes.
But using a different way, like random walk, right?
So this random walk is just to generate the sequence or segment. But for the NLP, they already have the sentence, so you don't need to do the random walk to generate a sequence of the word. You already have the sentence. But for this row network, we don't have the sequence of the row segment. So we do the random walk first to generate the sequence of the row segments. So this idea actually is not new. For the graph GNN in the early days, they also do this. But they don't call it. They call. I think I have like the deep walk. This they just use random walk to generate the sequence. Also the node to back. Those are early work. Use this idea.
Okay, thank you.
Okay, so this is a trajectory-based application. So due to the time, I think I escaped this. So I move to the next topic. So this topic is for region representation. So for this, my group also did quite some work on region kind of the spatial data. One thing is we want to find some region of interest. For example, we may do birth region detection. One application could be like if we consider the Uber application. if suddenly some region has a lot of Uber requests, we may want to detect such a region. So this is burst region detection. Then the region search is also find region of the interest. If a user interested in some region, then they may give us some query, say what kind of region they want to find. Then we want to find this region efficiently and effectively. Then we also do some region analysis. Like given some data for a region, say if we collect all the tweets for the campus of the, then we want to find out what people are talking about. We can do some topic modeling for all the tweets in this region. Also, we do some region topic exploration. Then the topic I want to share is for learning region representation. Then after we have the representation, then we can support different downstream tasks. So this urban representation learning is try to learn some also a vector to represent a region. Then after we have the vector representation, then we can support the different downstream tasks. So the data source we can have for a region, it could be like the point interest, could be a trajectory, could be the satellite image, could be a street view. It could be other kind of data related to a region. Then for the this type of work, what we want to do is given this different type of data for a region, we want to learn a model to represent a region. Then from the model, we can get a representation. Basically, it's a vector representation for a region. Then after that, we can support the different downstream tasks. So here we give two examples here. The first one is land use inference. Like given a region, we want to know if the region is a commercial region or is a residential region or some other regions. Then the population density estimation is like after we learn the region representation, then we can estimate the population for the region. Other similar tasks maybe like you can estimate the property price for the region. Then for our work, before our work, actually there's quite a few papers on this topic. So later on we give you a short review for those papers. But our work, we also use a new type of the data. So it's from the OpenStreetMap. The type of data is buildings. More formally, we call it the building footprints. You can consider it's a 2D building polygon on the OpenStreetMap. It also contains some other information like the size of the polygon, the height, the tab, but it may not be available for every building. Then we also introduce the term building groups. It's basically just a collection of the buildings in OpenStreetMap. One way we can get a building group is we can just use the neural network to partition the buildings into the different groups. Each group we call one building group. So this is why we want to use this building group. So the one reason is it could be an effective type of information for modeling regions. So this figure gives you some intuitive idea so why it may work. So from the OpenStreetMap, we find for these two are all industry areas. You can see they share some similar patterns. Then these two are residential areas. You can also see they share some similar patterns, but also they are different from the industry areas. So it's one reason they may provide some useful information for representing regions. The other main reason we want to use it is because it's available in OpenStreetMap. And for OpenStreetMap, it has the information for almost every country in the world. So it means if you this technique works, you can use this to almost all the countries. This slide, I want to give you the literature review on this topic, region representation. In CS, I think is the first paper on this topic is published in 2012 in KDD conference. But before this one, actually in GIS community, they have worked a lot on this topic. When they first proposed this problem, they also consider it a task-specific learning task. So in other words, use a supervised learning method to solve this problem. So they just target one particular application. For example, they may just want to infer the function of each region. Then they train a supervised model to predict the function of each region. After the first work, then in the next several years, a few papers are published. They all follow this framework. It's a supervised learning. But in 2017, this second paper, it's the first paper. They consider this problem as in a different paradigm. So they try to learn a general representation for regions. After that, they use representation to support different downstream tasks. Subsequently, the people, they just try to use different type of data, different modality of the data to represent regions, such as POI data, mobility data. But for all this work, they are heavily rely on the mobility data. They assume they have the user trajectory in a city. But this trajectory data is not always available. Normally, they only get this data for very few cities, like New York City. They have some public trajectory data. Then they can use to learn representation for regions in New York City. But in many other cities, they don't have the trajectory data. So here is a list of the representative methods for region representation. You can see most of them use trajectory data. So this last one is our work. We use building footprint and we use POI. So both are public available data. But we don't use trajectory data. So for this previous work, they heavily rely on the trajectory data. Then the other issue with previous work is when they learn representation, they will ignore those data sparse area. For this, for example, if this area don't have any point interest or don't have any road, then they may just ignore this region. But however, this region also carry a very useful information to represent this region. Another issue is for the previous work, they use a fixed region partition scheme. But if a different application needs a different partition scheme, then they cannot be used. For example, if we say for one application, like if we want to do the land use inference, we may say use a different granularity for the partition. But if we have a different application like the population estimation, we may have the different partitioning scheme. Then previous work, you have to train a different model. So this is our method. What we try to do is we first just partition the city into the building groups based on the road network. So for this part, one new idea is for those empty region without any point of interest, we try to put some random point. Then we may want to learn the representation for the region using those synthetic points we add. Then the second part is we encode the building groups. Also, we consider the POIs, also those random points we generate from the first phase. Then, so this part is based on a transformer model. We do the encoding. Then the next part is we train the encoder with contrastive learning. So it's a very popular and self-supervised learning task. So if you use contrastive learning, then the most important thing is you need to find the positive pair and negative pairs. Very likely you need to do some data augmentation to get those positive pair or negative pair. So for our work, we do 2 levels of contrastive learning. So one is just based on the building group. Then we drop off some buildings from the building group as a positive pair. Then we randomly choose a different building group as a negative pair. So we use this to do the contrastive learning. Basically, we want to learn the representation so that this positive pair, the representation are close to each other, but they are different from the negative example. Then for the region level, we also do the contrastive learning. We also need to generate the positive pair and negative pair. So for this one, to generate the positive pair is if we use this grid as a region, we try to move the grid to a nearby one to make sure they have some overlap. We use this as a positive pair. Then we will generate some negative pair. So for the contrastive learning, we want to make the positive pair to be close to each other based on the representation. So this is how we want to learn the representation for the regions. After we have the representation, we can support the different downstream tasks. So the first one is land use inference. So again, for this task, we need some label data. So what we have is for each region, we have some vector representation for each region. Then we need to have some training data. For some region, we need to know their land use. Maybe say some region 50% for residential, 50% for commercial. Then we need some such a training data to train a model. Then we can use a model to infer the land use for other regions. So this is what we did. So this is a baseline method. So this is our method. Then the second task we test is population estimation. So for this one is we also need some label data for training. So for some region, we need to know their population. Then we use such a data to train the model. Then we use a model to other regions to estimate the population for those regions. We also do some visualization for the result. For each region, we get a vector. Then we just do a k-means for those vector. Then after we class them into several clusters. So this ground truth land use. So this we do this for regions in Singapore. So this is our method. Then this, if we just use a transformer to learn the representation, then we do the k-means. Then we can find for our method, we learn this representation, then it's more close to the ground truth. So this just for this one actually is just self-supervised learning. We get the representation. Then after we have the representation, we do clustering. Okay, so this second task about region representation. So this task actually is a very classic task in GIS community. Before I move to the next part, any question for this part?
I just want to ask, how do you evaluate the features that you learned from the contrastive learning? Like, do you just directly fine-tune the model from the contrastive learning, pre-trained model, or do you just use like a percentage of labels, like 50%, 60% of labels to fine-tune the?
For our work, we don't fine-tune the model. So again, it's similar to the, we just use a self-supervised learning to learn the representation for each region. For the self-supervised learning part, we use contrastive learning. But after we have the representation for each region, when we apply this representation for downstream tasks, for example, the population estimation, we don't fine-tune the model. We just take the region representation and the population as a label, as an input to some supervisor model like the neural network. Then we just use this one to, after we have the model, we apply the model to other region to predict the population. We don't fine-tune.
I'm using a time series and I'm exploring these self-supervised methods like contrastive learning in time series, and they usually fine-tune with like a few percentage of labeled data. So do you have any tips for time series, like using this contrastive method on time series? Like how to generate positive, negative pairs effectively for?
So your question is if you apply on time series data?
Yeah, like basically irregular clinical time series.
So if you want to see, I think a lot of work has been done for the train the model for time series data. They also use all kinds of the techniques like the transformer, the RNN, and also the contrastive learning. Also, there's a different work. I think most of the work I think for time series still they just focus on one task. They learn some model for this one particular task. I think for time at least 2 or 3 years ago, I think normally they do that way. Like if they do the prediction, then they just learn some model like you can use RN like LSTM or transformer. Then after that you can do the prediction. But recently I think there's some paper from the Alibaba group. They also apply this idea large language model for time series data. Then they do the fine tune. Then they also learn the representation. After they have the representation, they fine tune. Then they want to use this one to solve the different tasks for time series, like the prediction, anomaly detection. There's a paper from Alibaba. If you are interested, you can find the paper.
Sure. Thank you.
Also, a lot of paper. That paper is published in either KDD this year or CIGAR. I cannot remember. But on archive, I think a lot of the trial on doing the large language model for time series data. If you are interested, you can find quite some of them. Okay, let me say the final part of my tutorial today. Oh, we are running out of time. So this part is more about the foundation model. So this feature for the foundation model, the one is it should be a self-supervised pre-training model. The second one is normally it should be a task. It can be applied to multiple tasks after you have the model. Also should be able to handle internet scale of data and easy to deploy for downstream application. Perhaps you only need a fine-tune or zero-shot learning. So for the foundation model, before the foundation model, like we have the task-specific model. So this is for NLP. For each NLP task, you have some models. But for the foundation model, it's like we have the ChatGPT. Then we maybe only do a few-shot learning or zero-shot learning. Then we can solve the different tasks. So it's a paradigm shift. So this from the Hugging Face. Actually, you can get this kind of the figure from Google. You get a lot of such a figure. So foundation model appear in different domains like the NLP, the computer vision, the signal processing, reinforcement learning, they are all trying to build their own foundation models. Then natural question is for the, if we say we do research on geospatial data, I think many people will ask what ChatGPT can do for the geospatial data. Like if a database researcher, we also ask what ChatGPT can do for database research. Then to answer this question, we do some preliminary evaluation, like if we try to use this foundation model for the different geospatial problems, how is the performance? So we consider 4 types of the geospatial tasks. The first one is we call it geospatial semantics. The second is urban geography. The third one is health geography. The last one is for the remote sensing data. So for each area, we choose 2 tasks. Then we compare those foundation model and those task-specific model to see to compare their performance, to understand how well the foundation model can perform on this task. Due to the time, I think I cannot cover all the tasks here. Maybe I just cover the first geospatial semantics. So this GIS task, but it's more very similar to NLP task. So one is typo name recognition. The other is location description recognition. So the difference is for the typo name, we try to extract the larger geographical name, like the city or region or state. But for this one, it's more like a point interest kind of the location. So to use GPT, then we need give some prompt. So here we can design some instruction. So of course, the instruction you design definitely will affect the evaluation result. So this evaluation result is just based on the prompt or instruction we design. We, of course, we try a lot of the options that try to tune the prompt to get a good result as much as we can. Also, another thing I want to mention, the ChatGPT actually they keep fine-tune their own model. So maybe a few days ago you try something, it give you a wrong answer. Then a few days later it give you a correct answer. So that means that this evaluation may be only valid at the time when we test the model, but it may not be valid now. But anyway, it gives you some sense how well the foundation model can achieve on those geographical tasks. So this, for these 2 tasks, this typo name recognition, the other is location description recognition. Then we use, like the GPT, we use few short example for training. Then for this location description recognition, we can see the result here. So for this part is for a foundation model. So for this ABC, they are the task-specific model. Then for this particular task, we can see for this foundation model, you can achieve the best result, even if we only give a very few short example for fine-tuning the large language model. Then the second task here I have is for the it's a more like a time series prediction, but this related to this time series is related to a location, but it's a very simple time series. Then for this prediction task, we find the large language model can also outperform those classic model like ARIMA. But for this one, we don't consider a very advanced baseline here. Also, all the experiments here, they are performed on the same test data. Then we also have some other tasks. Basically, it's just we find a different task, then we try to compare the result from the ChatGPT with those task-specific solution. So for this one, so this ChatGPT result, so this specialized solution. Then for this task, the specialized solution outperform the result from ChatGPT kind of foundation model. So this is another task. It also from the image we predict if the neighborhood is a quiet neighborhood or noisy neighborhood. So for this one, also those specially designed model perform slightly better than those foundational models. So this is some other task. Then one task is the ChatGPT perform particular words is we give a location name. We want to do the geopassing. Geopassing means we want to infer the coordinates for the location. Then for this task, foundation model perform very bad. Based on our observation, we find those if the task involve a multiple data model, the ChatGPT kind of a foundation model may not perform that well. But if it's just one data modality, for example, natural language kind of a task, then ChatGPT normally can get excellent result. So for example, this task actually they involve two modality. One is text, the other one is geospatial location. Then the ChatGPT kind of the foundation model cannot perform that well. Then based on this preliminary experimental study, then we have this vision for our research. So this is also what my group is working on. So we aim to build this city foundation model. We want to use multi-modal data. For example, maybe a trajectory data, maybe a POI data, image data, satellite image data. This is a different modality. We want to train the city foundation model. Then after we have this model, hopefully we can solve the different tasks. ChatGPT can be used to solve different tasks. For example, after we have this city foundation model, maybe you can answer a question like this one: where's the nearest hospital? How is the region used? Then to address this issue, then what is the challenge? So compared to other areas, we find the geospatial domain is a slower adoption of the foundation model. The one challenge is for the data, it comes from the multi-modality. For example, we have the text data. Even for the geospatial property, it may come in different forms. Like we have the point location, we have the polyline, we have the polygon. Also, we have the image. We have all the different type of data. How we can learn a model from all these different modality of data. Then the other main challenge is data source. So it's different from the natural language. You can get a lot from the web. For the city, data is normally owned by different companies. For example, Google Maps, they have their own data. The Uber, they have their own data. Like the telecom company, they have their own data. So normally they don't want to share this share the data. So in our work, then we try to use OpenStreetMap to address this data issue because it's open data also contain a lot of the data we can train the model. So basically what we want to achieve is we want to use a different data source, and we have a model. Then after that, we can support the different tasks. We have a paper. This is a paper we already put in archive. If you are interested, you can refer to the paper. So finally, the work is most of the work is done by my student or my collaborator. So I thanks them for their contribution. So any question?
My question for the foundation model of your geoinformation task. The first one is, did you fine-tune this large language model for your specific task?
For our work, actually, we don't based on the existing large language model. Like we don't fine tune like existing large language model.
Yeah.
So instead, we just build our own. For the text part, we may use embedding from those existing large language model as input.
Yeah.
But we don't fine tune them. We just build our own model.
So it's like you just extract embeddings just directly from the large language model and as your input of your model and perform the tasks, right? Okay. So the second.
Yeah, for the text, we just use embedding from any language model as an input. For example, we can use from BERT or from the other, like the CLIP or some other model. But our main thing is not to learn representation for the word. We want to learn the representation for the city things. So then we design some self-supervised learning task to learn the representation for the city entities.
Yeah. Okay.
Yeah, that's what we did in our work.
Okay. So directly on the and you see
Yeah,
on the
yeah.
GPT-3.
Yeah, we don't fine tune like GPT-3 or Lambda. We just train our own model. But of course, our scale cannot be that big. We just with our available computational resources, we try to train our own model.
All right. Okay. So the second question is, what do you think the challenges of apply a domain-specific large language model? What's the challenge of build a domain-specific large language model like that?
Yeah, I think the challenge, in general, I think the challenge, one is the data, the other one is computational resources. So I think it's the two most important aspects. But if I say consider, if we go more deep for your question, I think a very good question. Then, if you want to say a general domain, like I think it's it's a word of the big company. From the academia, we really cannot do much, I think. But for the specific domain, like a city or some other domain, like time series or some medical domain or more specialized domain, like the maybe a lawyer. Or so. I think it's still a chance you can build a domain-specific large language model. But the thing is that there may be at least two ways to do that. One is that you fine-tune existing model, like you use a Lambda 2, then you fine-tune, use your data to fine-tune. The other one is you can build from scratch. I think these are two ways. Each one has a pro and cons. So it's hard to say which one is better. Have case by case, I think.
Okay, great. Thank you.